Every year, the world spends over $200 billion on just one thing: tires. This is a colossal sum, even larger than the entire economies of some of the world's wealthiest nations. The black, dust-covered rubber you see every day is actually a money-making empire and the lifeblood of the global economy. So why do these seemingly simple rubber rings have such immense power to manipulate money? What secrets lie behind this multi-billion-dollar industry? Let's unravel the mystery. Today, tires are so ubiquitous that we rarely think about the fact that they are actually a relatively new invention in human history. Surprisingly, wheels have been used by humans for about 5,000 years, but for much of that time, what we call tires didn't exist. Ancient carriages, horse-drawn carts, and even the first automobiles traveled on wooden or metal-covered wheels, resulting in bumpy and uncomfortable rides. Things began to change in 1839 when Charles Goodyear stumbled upon the vulcanization of rubber. Before that, natural rubber was almost useless for transportation because it was soft and mushy in the summer, but hard and cracked in the winter. This invention transformed rubber into a durable material capable of withstanding the harsh conditions of the road. However, the history of modern tires has also been heavily influenced by warfare. During World War II, the supply of natural rubber from Southeast Asia was severely disrupted, forcing the United States and many other nations to invest billions of dollars in developing synthetic rubber. This resulted in an industrial revolution, enabling tire production on an unprecedented scale. Today, most tires in the world are a combination of natural and synthetic rubber, a technology born from both scientific serendipity and historical pressure. Before official production begins, each tire undergoes an extensive development phase in a digital environment. Engineers use simulation software to build and refine every element, from overall shape and internal structure to tread design and rubber composition. The goal is to create a balance between grip, wear resistance, load capacity, stability, and ride comfort. Before appearing on the production line, the entire design is tested and evaluated through a series of in-depth simulations. Before a tire can withstand thousands of miles of rolling on the road, its journey begins with the milky white sap flowing from the trunk of a rubber tree. Much of the world's natural rubber comes from tropical plantations in Thailand, Indonesia, and Malaysia, where the year-round hot and humid climate provides ideal conditions for rubber tree growth. There, workers use specialized knives to make thin cuts in the bark, enough to access the sap-conducting system inside but without damaging the wood. Each drop of latex is then collected in small cups attached to the base of the tree trunk. To prevent solidification during transport, the rubber sap is often treated with ammonia before being sent to the factory. There, it is concentrated, rolled into thin sheets, and dried to create natural rubber. However, this material is only one part of the modern tire manufacturing process. Synthetic rubber, created through the polymerization of compounds such as butadiene, styrene, and isoprene derived from petroleum and natural gas, is also incorporated. Thanks to its abrasion resistance, cold resistance, and high stability, synthetic rubber now accounts for more than 60% of the weight of many modern tires. Few realize that the familiar black color of tires isn't actually the natural color of the rubber. In its initial state, rubber is off-white. To transform it into a material capable of withstanding heavy loads, constant friction, and extreme road temperatures, manufacturers must combine many different components in a tightly controlled formula. This mixture includes natural rubber, synthetic rubber, carbon black, along with plasticizers, sulfur, and various specialized additives. During the mixing stage, more than 30 components are precisely measured. Carbon black increases durability and wear resistance, while plasticizers maintain the material's flexibility and elasticity. The remaining additives are used to adjust many important properties such as processing temperature, curing time, and the hardness of the finished product. After being measured, all the raw materials are fed into high-capacity mixers operating under high temperature and pressure. In just about 5 minutes, they were transformed into a uniform block of black rubber, ready for the next shaping steps. The process of creating the main components of a tire begins with sheets of fully mixed rubber. These are passed through a continuous rolling system to achieve the precise thickness, typically only about 0.04 to 0.12 inches depending on the tire section, before being rolled into uniform layers. Next, a layer of high-strength synthetic fiber is fed into the rubber coating line. Under the influence of temperatures around 300 degrees Fahrenheit and tightly controlled pressure, the rubber becomes pliable and wraps around both sides of the fiber layer, creating a strong bond between the elastic material and the inner reinforcement layer. Simultaneously, thousands of ultrafine steel wires are arranged parallel with very high precision. After being wrapped and tightly pressed into the rubber, they form a crucial load-bearing framework, helping the tire maintain its shape, withstand heavy loads, and operate stably even at high speeds. Once all components are fully prepared, from the airtight inner rubber layer to the precisely machined fiber reinforcement layers and steel belts, the assembly process of the tire structure officially begins. On a large forming drum, an automated system sequentially combines more than 10 separate components in the correct design sequence. Each layer of rubber is fed onto the drum surface by a precisely controlled servo system, then pressed tightly against the layers below to form a uniform structure. Throughout this process, industrial cameras and force sensors continuously monitor the material's position to detect early defects such as misalignment, creases, or unwanted overlapping. After the material layers are completely assembled, compressed air is pumped inside. Under the influence of pressure, the soft material mass gradually expands and transforms into the three-dimensional shape of a real tire. This is the moment when the individual components begin to function as a unified structure. In the tire manufacturing industry, products at this stage are called green tires. Although they have taken shape and often weigh up to 30 pounds, they are still soft, lack tread, and do not possess the characteristic durability of a finished tire. Although already shaped like a complete tire, the raw tire is not yet strong enough to withstand the weight of a vehicle, nor does it possess the necessary wear resistance or grip. To transform this soft material into a product capable of lasting tens of thousands of miles on the road, it must undergo the most crucial step in the entire manufacturing process: vulcanization. At this stage, the raw tire is placed inside a large, two-part, enclosed metal mold. The inner surface of the mold contains all the grooves and negative details that will create the final pattern on the tire. The internal temperature is raised to over 300 degrees Fahrenheit, while compressed air or superheated liquid is pumped into an elastic rubber pouch inside the tire. The internal pressure presses the soft rubber against each small detail of the mold. The vulcanization process typically takes about 10 to 15 minutes. During this time, sulfur creates chemical bonds between the polymer chains, transforming the soft rubber into a resilient and durable structure. After the vulcanization process is complete and the tire is removed from the mold, it still retains some heat from the manufacturing process. Although it has taken its final shape, it must still pass a series of rigorous tests before being allowed to leave the factory. The inspection process usually begins with an automated measurement system. High-precision laser scanners examine the entire tire surface to check for roundness, concentricity, and the geometric dimensions of each area. Next, the tire is mounted on a specialized rotating axle and inflated to a pressure higher than normal operating conditions. This test helps assess pressure holding capacity, structural stability, and detect leaks invisible to the naked eye. In many modern factories, X-ray technology is also used to observe the inner layers of material. Defects such as misalignment of the plies, separation, or hidden defects can be detected before the product leaves the factory. Only tires that pass this entire process are certified as meeting the standards and are ready for real-world operation. Each year, billions of tires reach the end of their lifespan after having traveled tens or even hundreds of thousands of miles. Unlike many other materials, tires are difficult to decompose naturally because they are made of synthetic rubber, mineral oil, steel, and many highly durable chemical compounds. When improperly buried or disposed of, they can persist for decades and create negative impacts on the environment. Burning tires outdoors can release hazardous pollutants such as benzene and dioxins, while natural weathering can create microplastic particles that enter the soil, water sources, and surrounding ecosystems. To minimize this waste, many countries have invested in modern tire recycling technologies. After collection, old tires are crushed into small rubber particles, separated from the steel and reinforcing fibers before undergoing mechanical and chemical processing to partially restore the original material properties. The recycled rubber obtained is often used in the inner layers of new tires where high wear resistance is not required. Although the percentage of recycled material in a modern tire is typically only around 10 to 20%, this is a significant step forward in reducing the need for new materials and limiting the amount of tires discarded into the environment each year. From the white sap flowing down the trunk of a rubber tree to the automated production lines operating with near-perfect precision, each tire is the result of materials science, mechanical engineering, and dozens of complex manufacturing processes. If you found this journey interesting, please leave a comment letting us know what topic you'd like to explore next. Don't forget to like, subscribe to the channel, and turn on notifications so you don't miss fascinating stories about technology, engineering, and seemingly ordinary but extraordinary things. See you in the next video.